Hello everybody and welcome to this lecture on high temperature thermal energy storage. Storage is a very important element for the transformation of our energy system towards a clean and sustainable future. With an increasing share of fluctuating renewable energy in the grid, the demand of storage will rise dramatically. In the lecture on solar thermal power plants, I have already explained that in solar thermal power plants, the integration of storage systems is particularly easy and cost-effective. This is achieved by integrating the storage on the thermal side of the process and not on the electrical side. This requires high-temperature storage technologies, which we will take a closer look at in this lecture. First, we will briefly deal with the basics. Then we will take another look at the storage systems that are currently used in solar thermal power plants. And in the third chapter, we will then cover other very interesting and promising applications of high-temperature storage systems. First, let's look now at the basic definition for a thermal storage. In a thermal storage, we increase the energy content of the storage by adding heat. The energy can then be stored in the storage containment for a period of time, and when needed, the heat can be released again. So the thermal storage is characterized by the fact that heat is supplied to the storage during loading and removed from the storage during unloading. This, first of all, doesn't say anything about the storage principle itself. The different storage principles that are of interest here are listed in the categorization table on the bottom left. The principle can be, for example, a sensible storage. Here heat is stored by a sensible change in the temperature of the storage medium. Secondly, we got the latent storage. Here the storage medium undergoes a phase change and thus absorbs or releases the heat. And finally, chemical storage. Here the supply of heat triggers a chemical reaction of the storage material. Storage units can also be subdivided according to the process of heat input and output as shown here on the bottom right. The heat input or output can be either direct or indirect. Direct means that the storage medium is the same as the heat transfer medium. It is heated outside the storage tank directly in the process, and then the medium is fed into the storage tank for storing. A well-known example for this is the typical hot water storage tank of a solar system, where the water is heated in the collector and then filled directly into the hot water storage tank. Indirect means that the storage medium and heat transfer medium are not the same. This means that the heat has to be transferred from the heat transfer medium to the storage medium. This becomes necessary when the heat transfer medium itself is not suitable for storing, for example, if this would only be possible under high pressure, as it is the case with water vapor. The heat transfer in an indirect storage system always implies a temperature loss, because heat transfer always requires a temperature difference. Another criterion for classifying heat storage is the temperature range, where we differentiate between low and high temperature. Usually the high temperature range already starts at 100 degrees C, however we are dealing here with storage systems at much higher temperatures. And the fourth category into which storage systems can be classified is the duration of the storage cycle, meaning the period over which the storage is charged and discharged. Thermal storage systems are rather in the short and medium-term range. Long-term storage, such as seasonal heat storage, is difficult to implement at this temperature level. Besides some technical challenges, this is mainly due to economics. If a storage is charged and discharged completely only once a year, like with a seasonal storage, it must be extremely cheap. So far, this is only the case for a few low-temperature storage technologies, such as hot water. Let us now turn to the basic thermodynamic equations, which are relatively simple for a thermal storage. First, of course, there is the first law of thermodynamics. This law says that the addition or removal of heat and work changes the internal energy of the medium to the same degree. Since no work is done in a thermal storage, the equation reduces to delta Q equals delta U, and delta U stands for the change in internal energy. In case of a sensible storage, the addition of heat causes a change in the temperature of the medium. Thus, the change in heat is equal to delta T multiplied by the mass and the heat capacity Cp of the medium. Hence, the heat is stored by a change in temperature. The situation is different with latent heat storage. Here, the supply or removal of heat does not lead to a temperature increase, but to a phase change, which usually takes place at constant temperature. The energy required for the phase change is called the enthalpy of vaporization or enthalpy of condensation if the phase transition is from liquid to gas or vice versa. If the phase transition is from solid to liquid, it is called enthalpy of fusion or enthalpy of crystallization. For heat storage applications, the phase transition from solid to liquid is typically used since steam can only be stored relatively difficult in contrast to liquid and solid media. In the case of thermochemical storage, a chemical-physical reaction, which can be described by the enthalpy of reaction, is initiated by the supply or removal of heat. At high temperatures, thermochemical storage systems have so far only been used in laboratory scale and therefore do currently not play a major role in the heat storage market. And therefore, we will not deal with this storage approach in this lecture. In large-scale applications, we currently only see sensible heat storage systems. Along with the heat input or output to or from the storage, the storage capacity E is an important parameter. E is the amount of energy stored. It is the sum of the total amount of energy transferred to the storage and is just another form of the first law of thermodynamics, which is here applied to a complete charging or discharging cycle. In case of a sensible storage, it is calculated from the temperature difference of the storage medium in the loaded and the unloaded state, multiplied by the mass of the storage and the specific heat capacity. Another important performance indicator is the storage efficiency, which is calculated from the quotient of the heat extracted from the storage tank and the heat supplied into the storage tank. The losses included here are mainly the heat losses through the outer surface, which depends on the size of the surface, the storage insulation, the temperature, and the storage duration. Relevant storage media are listed in the following tables. In the category of high-temperature liquid heat storage, oils and liquid salts are mostly used. In the range up to 400 degrees C, these are primarily oils. For the range above that, salts are mostly suitable because oils are no longer stable at these high temperatures. Salt, on the other hand, has the disadvantage that it freezes at relatively high temperatures, so that auxiliary energy must be used to keep it liquid during longer downtimes. Material properties, temperature application range, and rough cost data can be found in the table on this slide. Depending on the application, liquid storage media are well suited for direct storage systems. For solid media, we see a variety of different media, such as concrete, ceramic, and sand, to name only a few. The big advantage of solid media is that some of them can be used at very high temperatures and that they are very cheap. As an example, I would like to mention sand, which can be used up to 900 degrees C and with storage costs of about only $0.05 per kilowatt hour thermally, it is by far the cheapest storage medium available. However, it must be noted here that solid media are generally only suitable as indirect storage media, so that a higher equipment effort is required for the heat transfer.